this video, I'm going to show how a separately excited DC generator builds up voltage and determines polarity. So in the diagram, I've got my field poles. I will draw a separate DC source. Remember, this is a separately excited generator, or the field excitation is coming from a separate independent DC source. So I'm going to draw my battery, and the negative is going to come out of this side. And this will be the positive. Okay, so I'm going to draw the field pole windings. So I'm going to come off my negative because the current is going to come out of the negative of the power supply. So I'm going to use blue. So I'm going to come off the negative, and I'm going to wind this around the left field pole, and then it's going to come around, and I'm going to wind it in the same relative direction around this field pole, so I get the same direction of flux. So this has to go under. And then it will come back to the source. So if we look at the direction of current, current is coming out of the negative and going this way. So it's coming up, and I'll put an arrow here to show the current. It's coming up, and it's also coming up here and here. So now we're going to determine what the polarity of the field poles will be, the magnetic polarity. So we're going to use our left-hand rule for electromagnets, where our fingers go in the direction of current through the coil, and our thumb points in the direction of flux, or in the north direction. So current, north, so I will mark this point as north. Same thing happens on this side. Current goes up, thumb points north. So if that's north, that makes this south. So I will put a south pole here. Now I'm going to have a conductor that's going to be turning in the magnetic field. So I'll just draw a dotted line to signify that they're looped together. And then I'll bring this conductor here to a term. These would be obviously going through the slip ring, or the commutator and the brushes. But this conductor is going to be turning. And for now, standard rotation for generators is usually clockwise. Even though we can run them any direction we want, we like to show them going clockwise. So this conductor's going this way, and then when it comes back around, it's going this way. It's going in the clockwise direction. So this is my conductor that's going to be turning in the magnetic field, and that's going to induce a voltage between these 2 points. What I'm going to do is I'm going to draw a load, because in order for current to flow, obviously we need a closed circuit. So here's my load. It's just a resistor. We're not giving it any, we're not interested in any voltage values. We just want to know what direction is the current going to flow, so we can determine what is the polarity of the load going to be when we're turning it in the clockwise direction. So we've got our separately excited field. Current is going coming out of the negative. It's going up. We've determined this is north, this is south. So the flux, the flux is going in this direction. So we know that when we have a conductor cutting a magnetic field, we're going to induce an EMF. So we're going to use our left-hand rule for generators, where our thumb is the direction of the thrust. In this case, when it's turning clockwise, the thrust is up on this conductor, it's down on this conductor. So I'm going to analyze this side. My forefinger points in the direction of the flux. Well, it's going in this direction. And my middle finger is the direction of the current through the conductor. So when the current is coming out of the board or towards me like an arrow, we like to show it as a dot. So I'll put a dot here. And if this is a dot, current's coming out of here and coming back into the board there, we can use our left-hand rule here. So this conductor is moving down. The magnetic flux is still going in this direction, but now the current is going in the direction of my forefinger or into the board. So I'll put an X here. So the current is coming out here, and it's going through the load in this direction, and then going back to the source, and it's flowing around in a circle. So if the current is coming out of here, we know that the current coming out of the source makes that negative, therefore that is positive. So a very simple way to determine what the polarity of the armature conductors, we would call this the armature conductors, or we could call this A1, and we'll call this A2. And this point is negative and this point is positive. Well, what happens if I change direction of the prime mover? Remember, there's going to be a prime mover on a generator turning the generator. So if we change the direction of the prime mover, what will happen? Well, I've got to erase all these arrows. I'll erase the polarity for now. But one thing that's staying the same, this is a separately excited DC generator. We're using a separate DC source. We're going to leave it the same polarity. So the polarity of our field poles stay the same. But the rotation is going to change. So now we're going to, I'll draw a new arrow for the direction. So now we're going to go counterclockwise. We're still going to apply the left rule. Remember, we didn't change the field excitation. The flux is still going in that direction or from left to right. But when we apply the left-hand rule, well, this conductor is now going down. The flux is still going this way, but the current is now going into the board. So when it's going into the board, I'm going to draw an X and a dot on this side, because the current, if it's going into the board, it's coming around here and coming out. And the current is coming out of here and it's going through my load in this direction and back to the source in that direction. So now when the current is coming out of A2, that makes this negative and makes A1 positive in this case. So what happens when we change direction of rotation of a separately excited DC generator? Well, it will still build up voltage to my load, but the polarity of the output of that A1, A2, or the armature will change. If this was positive last time, now it's negative, and vice versa here. So again, we change the direction of the prime mover to get a change in polarity. Now, if I change the polarity of the field poles, well, you can probably guess what's going to happen. It should change polarity of the load again. But let's show that, and we can prove it with our left-hand rule. So I'm going to erase this. I'll erase that. So I'll make this positive. I'll just put another line here. And I'll make this negative. So now this terminal's negative, makes that positive. Current is going to come out of here, and it's going to come up. But now here it's going down. It's going down. It's coming back around here. It's going down and down. So now we're going to apply our left-hand rule. The current is the direction of my fingers, and my thumb is the direction of the flux. So that makes this a north pole. If that's north, this must be south. And again, left-hand rule, thumb points north. This is the north pole, south pole. Well, now the flux is going in this direction. Remember, I'm still turning counterclockwise. I better erase my current direction arrows and my polarity, because you can guess what's going to happen. We're going to apply the left-hand rule. Well, I have to stand up, so I can't turn my arm that much. So if it's going in the counterclockwise direction, it's easiest for me to see this side, where this conductor is going up. The flux is going in the direction of my finger. Therefore, my middle finger, the current is going into the board. If the current's going into the board, I'm going to put an X. And if that's an X, this must be a dot, or that's where the current is coming out of. So the current's coming out of here, going through my load this direction, and coming back here. So current comes out of this point. That makes this point negative and makes this point positive. So you can see with a separately excited generator, voltage builds up in either direction of rotation. I can change the polarity by changing direction or changing the polarity of my field poles.